All right, so this is Math 150, Section 1, Lecture 2. And so what we're going to do today is we're going to start talking about dot products and vectors. How many of you have not seen a vector before? Okay, is everybody fairly comfortable with vectors? So years ago when I was teaching differential equations, I was using clickers. And I asked students, how many of you are comfortable with 2x2 matrices? It's not a prereq for the course, but it's something that will make it a lot easier. And just absolute silence. Does anybody want a review of 2x2 matrices? Okay, well, in the differential equations class, I asked if people wanted a review, and nobody raised their hands. So this is much better that you all raised your hands. So I said, I'm going to ask the same question again with clickers. And I'm not going to tell you what the response is. I'm just curious. Something like 47% of people wanted a review of 2x2 matrices, but no one was willing to speak up. So almost surely, if there's something you want to see, other people will thank you for it. Not out loud, that'd be too easy, but they will be very grateful that it's brought up. So briefly with vectors, you normally think of a vector as having a magnitude and a direction. And then we get to choose what coordinate system we want to use when we write our vectors. So for the most part, we typically use Cartesian coordinates. So if I write, v is 3, 4, 5, this means 3 units in the direction of the x-axis, 4 units in the direction of y, 5 units in the direction of z. Normally we put arrows when we're writing things on the board to just remind you that it's a vector. Sometimes they use bold notation in books. Really doesn't matter what notation you use as long as you're consistent and as long as you can glance down and see what's being discussed. I like putting an arrow on vectors so I can quickly tell this is a vector. It's very easy to confuse different quantities. Okay, so it's very easy to confuse vectors and scalars. Scalars will be our real numbers or maybe the complex numbers. And the rules of vector addition are basically component-wise. So add component-wise. So if I give you w equals 8, negative 1, 4, then v plus w would be, I added components, so it would be 11. I would be 4 minus 1 is 3, and 5 plus 4 is 9. Sometimes people use square brackets rather than parentheses. It doesn't really make much of a difference. So the question is, what does a vector physically represent? Well, it's magnitude plus direction. So the book has some examples of using vectors to represent a force. And if you want to calculate what's the net force on an object, you add up all the forces and you see what's left over. Now, sometimes you can actually combine two vectors. So what we're really asking for is I want a binary operation that takes as input two vectors and spits out another input. So what are the possible outputs if I combine two vectors? So I take two vectors in. What's one possible output? What kind of object? So we input two vectors. And what's a possible output? What kind of object could come out? So I could have, here's my vector v, and I'll have them at the same base point. Here's a vector w. And I could talk about maybe the triangle spanned by them, or the parallelogram spanned by them. That would be the triangle. That would be the parallelogram. So that's one possibility. But we're going to be talking about this in the book. What quantity do we have today that takes two vectors as input? So you could make a matrix of the vectors, and this gets us into linear algebra, and there's a lot of stuff you can do there. But what's the big idea from today's lecture? Dot product. Dot product, right? So what is the output for the dot product? The output is a number. Later we'll see the cross product where the output is actually a vector. It turns out the cross product cannot be defined most of the time. Three-dimensional space is one of the few lucky situations. Did I close the door? Am I just this bad at closing doors? Okay, so let's look at the dot product. So if we have V is V1, V2, dot, dot, Vn, and W is W1, W2, dot, 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 Wn, then we define V dot W to be V1, W1 plus V2, W2 all the way down to Vn, Wn. And we can write this more concisely with summation notation. So we can write it as the sum, k goes from 1 to n, of Vk, Wk. And so this will be a number. And then the question is, what does this number represent? So it represents an angle. Or it has something to do with an angle. So what you want to do is you want to get a sense of the functional form of a quantity. That's going to be far more useful for you than the actual quantity. You want to get a sense of an object. So the formula we have is V dot W is the length of V times the length of W times the cosine of the angle between V and W. So if this is V and this is W and this is the angle between V and W, does it matter if I switch the order of V and W? Will that change the angle? I think it might change the angle by a negative sign, because we're now going in the opposite direction. So you have to be a little bit concerned. Well, let's look at the formula. It's going to be a cosine of the angle between them. Well, if I change an angle by taking the negative of it, do I change the cosine? No. So geometrically, this quantity will be very nice. So what you want to do to try to get a feel for what something is like is you want to look at special cases, or you want to see what the formula looks like. If I were to rescale V by a factor of 5, what happens to the left-hand side of the equation if I increase V by a factor of 5? It increases by a factor of 5. What happens on the right-hand side? It also increases by a factor of 5. So the length of a vector is just V1 squared plus V2 squared all the way to Vn squared, and then take the square root. Or conversely, it's the square root of V dotted with V. So when we look at this formula, if I rescale V by a factor of 5, both sides change by a factor of 5. If I rescale W by a factor of 2, both sides rescale by a factor of 2. If I solve for cosine of theta, I get cosine of theta VW is going to be V dot W over the length of V, the length of W. Well, that's good, because if I were to change the length of these two vectors, that shouldn't change the angle between them. And so this formula already begins to have some nice properties. If you could choose any direction for V, what direction would you choose for V initially? So if you could choose a direction for V, what direction would you choose? What do you think might make things simple? I'm sorry? No, I'm asking for the V. What direction might you want to choose for the vector V?
Positive.
Okay, what do you mean by positive?
Like going, I guess, to the right.
Going to the right, along the x-axis.
Yeah.
So choose V in the x direction. And now if you think of what's going on, here's V. What size would you want to choose for V? What would be a good size for V? Yes?
Probably a magnitude of 1.
Magnitude of 1. Make it unit length. There's a lot of formulas where you have to take into account the magnitudes. If the magnitude is 1, then you don't have to worry about, well, did I forget to include it? It's 1. So choose V in x direction, unit length. So So this would be the vector maybe 1, 0, 0. Now if you look at what's going on with W, here's W. So now if you look at V dot W, say W is W1, W2, W3. If I look at V dot W, I'm going to just get the component of W in this direction. Let's go in 2 dimensions first. Let's imagine we're just in 2 dimensions. So V is now 0, 1, and W is W1, W2. So in this case, if I do V dot W, I just get W1. Well, if you look at this right triangle over here, this is W1, this is W2, and then this would be the square root of W1 squared plus W2 squared. So if I then look at V dot W over the length of V, length of W, I will get the cosine of the angle between them. So in the special case, when my vector is along the x-axis, it's unit direction, I'm in 2 dimensions, I do get the geometric formula I'm hoping for. I do get that the cosine of the angle is just V dot W over the length of V, which is 1, and the length of W, which is the square root of W1 squared plus W2 squared. So this proves the dot product formula holds in this very special case. Now let's see how far we can push it. Does it really matter if V is unit length? No, we saw a moment ago that if I rescale V by a factor of 5, I change both sides by a factor of 5, so this ratio would be unchanged. So I can actually drop the unit length assumption. But I still am assuming that my vector is in the direction of the x-axis. That's a bigger assumption. What you would like to do, and this is where linear algebra would be helpful. So typically in this class, if I ever need a result, it's either linear algebra or real analysis. Linear algebra would allow us to then say that because this holds for a vector in the direction of the x-axis, it will hold in general by just rotating the entire coordinate system. But that would require us to do a bit of a linear algebra digression, which is a future class, so we're going to have to skip that for now. So let's try to show why this formula is true in general. Okay? The first thing is, does it always make sense to talk about the angle between 2 vectors? What if they're in 3-dimensional space, or 4 or 5? Well, if I give you 2 vectors, or maybe I'll do it like this, they're always going to be contained in a plane. If they're in the same direction, then I have a lot of different planes that can contain them. But if they're not in the same direction, I can still contain them in a plane. So it is well defined to talk about the angle between those 2 vectors. It's more convenient for us if the vectors happen to be in one of them in the x-axis, but we can't hold it in general. All right, so this seems to be a little bit too high right now. Let's try to make it. All right. So now the question becomes, how do we show that this formula holds in general? So we need the law of cosines. How many of you remember the law of cosines? It's for those who think the Pythagorean formula is not enough. All right, so what was the Pythagorean formula? So what's the Pythagorean formula? A squared plus b squared equals c squared if we have a right triangle. So now we need law of cosines. So here is some angle theta. Here is maybe A, B, and C. And then the law of cosines is c squared, I think, is a squared plus b squared minus 2ab cosine theta. Okay? How would we prove this? So how would we prove the law of cosines?
You draw down a right triangle.
Okay, so there's 2 ways I can grab right triangles.
Yeah, I was thinking like outwards, so like from like the top of it, and then just draw a line down.
So I could come down like this, And I could call this maybe the height, and I could call this x. And now how many right triangles do I have?
Now you have 2.
Now I have 2. Did you have another idea?
Yeah, I was going to say you could try drawing a line from the angle between A and C to B.
So here. So we have 2 different ways of doing it. And we would split B into B1, B2, and we would have some kind of height in there. To me, those are the 2 natural things to try. Any preference as to which one we try first? Whichever one we try, I'll leave the other one for you to do as a test. We'll try this one because it's drawn. It doesn't mean that the other one would not work, it's just this one is already drawn. So let's just repeatedly use Pythagoras. So we have a right triangle here, so we get c squared is h squared plus x squared. And then we also have b squared is h squared plus a plus x squared. Okay? So we see that there's a lot of things in common. So we get this, if we expand out, will be h squared plus a squared plus 2ax plus x squared. Well, h squared plus x squared is just c squared. So we would get b squared is c squared plus a squared plus 2ax. So the problem is we still have an x that's lurking and around here, right? So we have an angle here. We can write a is maybe b times, well, a plus x would be b cosine theta. So if we actually just kept it over here, a plus x is b cosine theta. Okay? But if we put this in and square it, things are now getting painful. Right? Because we want to just have a 2ab cosine theta. And now here, if we put this in and square it, we're going to be getting, a b squared cosine squared, which is not necessarily what we want. So I'm deliberately not trying to find the most efficient proof. I want to talk about how would you approach problems like this. At this point, what do you want to do? Yes? So we could replace x with a term that involves cosine. So we do have a hypotenuse c here. But the question is, what would this angle be in terms of that angle? So what I might want to do at this point is I might want to go backwards. And we had a suggestion for another approach. Maybe that approach will be better. So let's pause this proof, and let's look at the other way of adding the line. And it's often very difficult when you start an approach to just put it aside and say, well, maybe this will work, but I'm having some issues. Let me see if the other way looks a little bit better. So in this approach, here's theta. We'll draw a perpendicular here. We'll call this B1. We'll call this B2. We'll call this A. We'll call this C. And now we have a lot of right triangles. So we need a name for this. Do we want to use H? It's a different triangle. It's going to be completely different than the algebra there. Or do we want to use a different letter? What are your thoughts? I'd use a different letter. Let's use Y. So from this triangle, we would get B1 squared plus Y squared is A squared. from this one, we would get b2 squared plus y squared is c squared. Okay. And now we also have some, this is theta, so is there a way to get good lengths for things in terms of theta? What do you think? So we've got our right triangle over here. B1 would be a cosine theta. But this is not a whole full side. Right? We wanted to somehow get a term that was, twice AB cosine theta. So, which approach now do you think is better? Do we want to go back to this one? All right, so we'll go back to this one. All right, I'll have to play games with the heights later. So here we've got b squared is c squared plus a squared plus 2ax, or over here, okay. So if we just use this one, that would get us b squared is h squared, then a plus x is going to just be b cosine theta. So it'll be b squared cosine squared theta. Yes?
For the line where it says b squared is c, so yeah, that one.
Mm-hmm.
Can we replace x with b cos theta minus a?
Okay, so what you want to do is you want to say x is b cosine theta minus a. Ah. So now if we put that in here, we would get b squared is c squared plus a squared plus 2a, and then x would be b cosine theta minus a. That's looking very promising. Because now we're going to get a 2ab. We'll have a minus 2a squared. We have an a squared. So now we get b squared is c squared minus a squared plus 2ab cosine theta. And now if we bring everything over, we would get a squared plus b squared minus 2ab cosine theta is c squared. And so that will solve the algebra. So these are difficult problems to do. It comes down to figuring out what is the right way to look at things. So what made you make that substitution? It's the exact right one to do. What made you do that?
I just looked at the line and I saw a plus x, and I was like, oh, maybe we can replace x with b cos theta minus a.
And then what's really nice about that is we now get the cross term we're looking for. So make sure you send me an email. So we now have the law of cosines. And so the way you remember it is these are the two sides next to the angle. So when we're looking at what's going on here, here's the angle, here's a and b. And so it's a squared plus b squared minus twice ab cosine theta is the side opposite. So now let's see if we can do this and get the dot product. So for the dot product, we want to calculate lengths of objects. So we'll start off with two vectors, v and w, and then we'll try to find their length. So we can get rid of this one now. And so now, dot product proof. So here's V, here's W, and then what would this vector V be? What would this vector be over here, from here to here? So what would this vector be here? Yes? W minus V. So how would you know it's W minus V? Well, if I go from here to here and then here to here, my net motion is just W. Right? Because if I go here to here, here to here, I end up just moving W. Okay, well, if that's the case then V plus what equals W? It's got to be W minus V. So now we can apply the law of cosines. So apply law of cosines. So according to the law of cosines, the length of V squared plus the length of W squared minus 2 length of V, length of W, cosine theta VW is equal to the length of W minus V squared. I'm just using the law of cosines. So what is the length of V squared? Do we want to expand that out? So one thing we could do is we could say V is V1, V2, V3, Vn, and I could say that this is the sum of V1 squared plus V2 squared plus V3 squared, et cetera, et cetera, et cetera. Do you think I want to expand this out? No, because the goal is to reach, the cosine of theta VW is the length of V, is V dot W divided by the length of V, the length of W. So if that's what our goal is, it's probably not a good idea to expand this out in coordinates. So you really want to keep track of what you're trying to reach. Okay? And so let's try to do the calculation. So we'll keep the length of V squared as is. We'll keep the length of W squared as is. We've got minus 2VW cosine theta W. That's looking really good. So let's figure out what the length of W minus V squared is. All right? So the length of W minus V squared is W minus V dotted with W minus V. And this just goes back to our definition of length. The length of a vector is the sum of the squares of the components, square root. Since we want the length squared, we lose the square root. So all we're using right now is that the dot product is a convenient way to write the sum of the squares of the entries. Well, when we expand this out, what you eventually prove is that all the laws you want the dot product to have, it has. It's distributive, it's commutative. So this is the same as W dot W minus V dot W minus V. So I'm going to just do it slowly. So it'll be W dotted with W minus V, minus V dotted with W minus V. And now W dot W minus V, this will be W dot W minus W dot V minus V dot W minus V dot V. What's W dot W?
W squared.
Length of W squared. So this will just be the length of W squared plus the length of V squared minus 2 V dot W. Because the dot product is commutative. V dot W is the same as W dot V. V1 W1 is the same as W1 V1. So notice that this is looking a lot like what we want. We have over here length of V squared plus length of W squared. That will cancel with those. And then we have a minus 2VW cosine theta W is equal to negative 2 V dot W. So, yes?
I was just wondering if you could explain why the vector times the vector converts to the length of the vector.
Sure. So the length of V by Pythagoras is the square root of V1 squared plus V2 squared plus Vn squared. Well, this is the same as the square root of V dot V. Because when I take the dot product, I just get the sum of the squares of the entries.
Okay.
So this is just a convenient consequence of the dot product. It allows us to write lengths nicely. So now we can substitute back. And when we substitute, we'll get the length of V squared plus the length of W squared minus 2 length of V, length of W. If you think this is bad, I have to do it twice today. Cosine theta VW is the length of W squared plus the length of V squared minus 2 V dot W. All right, now we just have massive cancellations. The length of V squared cancels from both sides. The length of W squared cancels from both sides. The negative 2 cancels from both sides. And we're left with the cosine of theta VW is V dot W over the length of V, the length of W. And that's what we wanted to prove. So this completes the proof of the dot product. And so there is a geometric interpretation. So what are the two most important angles, if you could think of between two vectors? What would you love the angle to be? Yes?
90 or 0.
90 or 0. If it's 0, they're in the same direction. And if it's 90 degrees, they're perpendicular to each other. So what's great about this is if they're perpendicular to each other, cosine of theta is 0. So it means V dot W equals 0. So we get the following corollary. V is perpendicular to W. How many of you remember this symbol from geometry many, many years ago? Right. So this means perpendicular. If and only if V dot W is the number 0. So we now have a really good, simple test if two vectors are perpendicular. And is the argument here, is this only valid in 2 dimensions? Or is this argument valid in n dimensions?
Probably valid in n dimensions.
It's valid in n dimensions. I'm having a triangle, and I'm just saying law of cosines. The vector v and w lie in a plane. So I can use my triangle. Everything is fine. So the dot product is an absolutely wonderful result. It gives you a geometric interpretation for v dot w. And if you think about it, if I have two vectors, one of the most natural things I can do is just multiply them component by component. Now, instead of adding them, I could have had a new vector where the first component was v1, w1, the second component was v2, w2. We've chosen to create a number from two vectors. So we take as input two vectors, and as output we get a number. Why is this a good thing to do? This is why it's a good thing to do, because it has a good geometric interpretation. Okay, so one of the questions for today was, what does it mean to multiply vectors? There is another way to multiply vectors in 2 dimensions. That's the cross product, which we'll be getting to soon. As a rule of thumb, you can't take two vectors and get back another vector. In 3 dimensions, you can. And by considering 2 dimensions living inside 3 dimensions, you can do it there too. And so I'll quickly give a motivation of what the cross product is. We'll do more on that later. Is everybody comfortable with this proof? Okay. So the cross product, which we'll get to later, imagine here's V, here's W, and then this is where it's going to be really bad. V cross W would be coming straight out of the board. So the cross product is in the direction perpendicular to both V and W. Yes?
Can you take the cross product of two two-dimensional vectors, or wouldn't you have to
you can embed those two-dimensional vectors into a three-dimensional space. So if I have just two vectors in 2 dimensions, imagine their third component is 0. And then the cross product would be in the z direction. So in general, we can't combine 2 vectors and get another vector, but in 3 dimensions we can, because if I give you 2 directions, how many directions should there be in a 3-dimensional space?
3.
There should be 3. So I've got 2 directions right now. There's a unique direction perpendicular to both of them. If I live in 4-dimensional space, there's not a unique direction. There'd be 2 more directions I could go. And that's why we can really only do this in 3-dimensional space. So another one of the questions was, is it possible to find the angle between 2 vectors in 3-dimensional space? Yes. Exactly the same analysis works to find the angle in 3-dimensional space as 2. This is why I wanted to go through the proof without putting down coordinates. We could put down coordinates and have everything simplify at the end of the day. But given the structure of the formula we wanted, it was better not to do this. This is one of the hardest things to learn in mathematics, is when do you want to just roll up your sleeves and do brute force calculations, or when do you want to try to do things at a more theoretical, higher level stage? And if you can do that, you then get a result that's applicable in a great many places. So we now have the dot product at our disposal. Okay? Any other questions on the dot product? So technically, we want to prove things like the distributive property. How would you prove the distributive property? So we said, W dot W minus V is W dot W minus W dot V. How would we prove that? Yes?
Well, if you treat W minus V, I guess, as a vector,
Okay.
and then like the first component would be W1 minus V1 times W1. And then you can just keep going from there.
So basically, it's roll up your sleeves and just brute force it. How many times in your life do you think you have to brute force and do this proof? Once. And once you do it, you're done, you have the result. This should remind you of the rules from differentiation. The derivative of a sum is the sum of the derivatives. The derivative of a product is f prime g plus f g prime. You prove it once and then you can use it. So in this situation, I would have a1, a2, an dotted with b1 plus c1 dot 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 bn plus cn. Well, now, by the definition of the dot product, I can actually just go through and do the algebra. And so I would get a1 times b1 plus c1 plus dot 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 plus an bn plus cn. Now I can distribute these because these are just real numbers. So I would get a1 b1 plus a1 c1 all the way down to an bn plus an cn. And now I'll put all the a's with b's together and all the a's with c's together, and I'll get a1 b1 all the way down to an bn plus a1 c1 all the way down to an cn. All right? And now this is just a dot b plus a dot c. And that would be the proof. So that's the proof that the distributive law would hold. And then you can go through and you can prove that a dot b is the same as b dot a. You would just go through, expand everything out, and say, well, look, a1 times b1 is the same as b1 times a1. So a lot of times, unfortunately, the best way we have to prove things is to just roll up our sleeves and do the calculation. Sometimes people find this almost cathartic. It's not that bad, just having the algebra flow out. You always want to try to get a sense of why might this be true? Can you come up with a geometric interpretation as to why the dot product distributes? So what should the interpretation of A dot B plus C be? So is there an interpretation of what the dot product is? What does A dot B represent? It's going to be the cosine of the angle in between times the length of A, length of B. So you could try to see, can you come up with a story and interpret what's going on here? You know, that A dot B plus C, can I interpret this now as, well, this is going to be like the angle of between the vectors A and B plus C times the length of A, length of B plus C. So you could try to do that. Sometimes it's easier just to do the computation. Okay, any questions on how we would use the dot product to tell if two vectors are perpendicular? No, you just calculate and see if it's 0. Okay, any other questions on this section? Okay, so I want to end today with areas of triangles. So we did the area of a triangle, if it's right, was just 1/2 base times height. What if the triangle is not right? So area of triangles. So here, I'll call this base and height. So the area of this triangle should still be 1/2 base times height. So how many of you remember the proof or can prove that the area of this triangle is also 1/2 base times height? So the proof, amazingly, is similar to the proof we use for the law of cosines. What kind of triangles do we love?
Right triangles.
Right triangles. So when we put down this auxiliary line here, when we look at the height here, this generates two right triangles. Can we calculate the area of those two right triangles? Yeah. Let's call this length here x. So we'll have a big triangle. So the big area would be 1/2. The base is now b plus x times the height. And then the small area, the small triangle, would be 1/2 x times height. So the original triangle is just going to be the difference. So you have 1/2 b plus xh minus 1/2 xh, so you'll get 1/2 bh, which is what we wanted to show. So we've now seen this trick twice. And it always comes down to try to work whatever you're given to something you have knowledge about. How many of you have ever watched a presidential debate? How many of you notice that whatever question the candidate is asked, they kind of meander for a few seconds and then they move into their prepared bit? And the whole point is they just want to use whatever question you have as an opportunity to get to whatever they want to speak of. Over here, I know how to deal with right triangles. Whatever problem you give me, I'm going to manipulate and move it until I get a right triangle. Now, it may be difficult then to figure out what is the correct right triangle as opposed to what is the right triangle, because that just doesn't sound well English-wise. What is the correct right triangle to look at? You know, for the initial problem, we ended up making it work like this. Could we have made it work if instead we had gone up like that when we were doing the law of cosines? We still needed to be very clever to represent this. Maybe we could do the same way for something else. And so I'll leave that as an exercise. All right, so this is, I think, a good place to stop. We will continue on Wednesday. And then, again, if there are specific things you want me to incorporate, let me know.